So we want to look at how waves interact with different materials. So we're going to look at a fairly simple example where we look at a wave that's bouncing off of something. So here's a pulse going along a string, and notice what happens. Okay, so we have two different kinds of boundaries here. This top one is what's called sort of a free end. It can slide, whereas the bottom one is a fixed end. So when a fixed end happens, it reflects and turns over, whereas the free end allows for the wave to go up and reflect back in that way. So this picture from the book shows what happens for the pulse that you saw in the animation. In other words, when you have a fixed boundary condition, now the fixed boundary condition is on the top versus the free boundary condition. And the reason this becomes important is that if you have a whole bunch of waves coming to the right, so you have this pulse followed by, say, another pulse, then as this wave is coming back, it might encounter an upward pulse. And then we start to wonder what happens when we add waves together. So when we have two waves, we want to add them together. It's called the superposition of the waves. And so we can think about, if we take, say, a wave that's not very realistic, but we can start there because that's easiest when we're trying to add them up. And notice that when they start to overlap, like when this part overlaps with this part, we would have something that would be twice as high. Here's our overlap region. And then the rest of the wave would sort of be like this as they're coming together. This orange is the overlap region. And then finally, at some point, we would have something that is much bigger. There's the overlap region right here. It would be twice as big, the same width as when we started, and then the waves would pass through. And of course, my trying to draw it like this is not very helpful, so we will look at a simulation here. So here's a simulation of the two sort of artificial square wave pulses coming together, and you can see they're coming together and they add up, and then they keep going through each other. So this is not the most typical type of pulse we would use. Here's a more realistic Gaussian pulse coming together, and you can see they add up briefly to be twice as big, and then the two waves keep going through each other, so you just add them bit by bit. Here's what happens when one is high and when one is low, and notice when they start to overlap, right now they're going to overlap, and we get this when they're exactly overlapped. Notice they cancel each other out. This is called destructive interference. So this is an example of destructive interference. The first one, when they completely match up, is called constructive interference, where they add up together and you get this combination wave here. So right here, it's actually off screen, where they've added up and the height is actually twice the height of the two initial ones. And so that's how we start to understand how we can add waves together. So now we can add two waves coming at each other, these sinusoidal waves, and they add together in an interesting way. So this is what we call a standing wave, because it doesn't look like it's going to the left or the right. But if you notice, it's made up of a wave coming from the left and a wave coming from the right. Those waves coming together and then adding up, both constructively and destructively. So notice, here's where they're constructively added up, and then right here, they've canceled each other out. They're destructively added up, and in the next time step, they're completely constructively added together. And so this gives you a picture of how we get what's called a standing wave. And in particular, the way we get this is we put the two things that we we saw together, where we take a traveling wave, and you're going to notice what happens here is that this is going to hit the wall on the right and reflect. So this is like a hard barrier, and it's sending a wave that is opposite back. And so eventually, instead of looking like a wave that's just traveling to the left, we're going to see that this is a wave that is a standing wave. So we've built it by having two traveling waves coming at each other and then constructively and destructively interfering. So when I have these two waves sort of coming together, the thing that's got to be true for them to add up, and this is not drawn so nicely as a simulation, is that they need to have the same wavelength, right? The same wavelength. And if they're going to add up completely and then cancel each other out, they need to have the same amplitude, which is really easy to do if you start this on a string that is fixed at one end, and then you set this oscillation, right? And you do it with a set frequency. So you have a set frequency. So you're not changing the frequency. You're not suddenly going slower or quicker. You have a set frequency. This wave train makes it to the end where it's fixed, and then we have a wave train coming back the other way, and so we can have constructive interference, which would be when you take a wave like this, I want it to look the same, and add it to basically a duplicate. So you add these together, that gives you something that's twice, right? It's the same frequency, it's just twice the amplitude. That would be constructive interference. And destructive is when they're completely out of phase. So I have a wave like this, and it's completely matched by something out of phase, and so the summation of those, the sum of those parts would be destructive. Of course, these are very special conditions. Most of the time you have waves that can sort of add up. In some parts they match, and in some parts they don't. You can have one that's a little bit out of phase, and so you get some in-between cases. So most of the time we have not constructive or destructive, but something in between. But when we have this, that can lead to something that we saw that looks like a standing wave, where I had these two waves that were merging together, and then the sum of these two merging waves, which you can create by a wave bouncing off the wall, looks like a standing wave. And it's really hard to draw a standing wave here, but the way we can think about this, and we'll look at the properties of a standing wave, is that we tend to draw them like this, even though that's not what they actually look like. But what's really happening is that at one time it's at this position, at another time it's at this position, at another time the wave is at this position. And so overall, blurred out, averaged over time, we sort of see something like this, where we have some points where they don't oscillate at all. Sorry, that should meet on the line there. And some points where it goes from high to middle, then to low. And so this is our so-called standing wave that is made up of a left plus right going wave, where we've got the same frequency, so it's created by the same oscillation, same speed, which is easy if we're in the same material, right? The speed is determined by how tense the string is, and we need the same amplitude. Again, not too hard to generate if we're on the same string. Then this, and it's created by the same oscillator that's going at the same amplitude all the way along. So that is we're going to spend some time looking at standing waves, because this becomes pretty important for sound generation and a number of other applications, but we'll look at it primarily in sound.